So this video is part one of a two-part video on calculating moment of inertia. And so there will be a total of 3 different ways to calculate the moment of inertia. And this one will outline the first 2. So before we get to the first 2 methods, imagine that you have a system. For a system of objects or particles, then you can find the total moment of inertia for the system by just adding the individual moment of inertias. Remember what moment of inertia is. It's the resistance to change in an angular velocity, analogous to mass for linear world. And so in this case, we know that if we had a bunch of objects and particles together, the total mass would just be the sum of their masses, the sum of their linear inertias. Here it would be the sum of their rotational inertia. So it would just be I1 plus I2 plus I3 plus etc. So you just add the individual i's. So you just add the individual moment of inertias to get the total moment of inertia of a system. And as we've discussed previously, moment of inertia depends on not just mass, but also on the mass distribution. And so our equations for calculating moment of inertia will have to take into account not just the mass, but the mass distribution. So let's go ahead and talk about the first way. The first method is going to be the simplest, and that's going to be for that of discrete particles. So for discrete particles, the moment of inertia equation is simply going to be I is equal to the sum over all particles, I, of m sub I r sub I squared, where m sub I is the mass of some individual particle I, and r sub I is the distance that mass is from the axis. So this is actually a scalar value here, where r sub I is the distance from m sub I to the axis. It's a scalar quantity. It's simply a distance. And so for a system of particles, if I say draw out an example, here's my axis of, say, rotation. So things will rotate, around the axis this way. If I just sort of draw a bunch of particles in this plane, so I'll just draw particles in sort of random locations in this plane, so you can imagine them kind of rotating around as so. And I'll label this one M1. Then in this case, R for that M1 would just be this distance, that shortest distance from the particle to the axis. And the same thing is here. For that's M2, that'd be R2, and then R3 for M3. So it's really just the distance from the mass to the axis. And so the I would then be equal to just M1 R1 squared plus M2 R2 squared plus M3 R3 squared. And if there were more particles, then you would add those accordingly. So one thing to note with this first method is it can apply to discrete particles. We can also note that uniform objects have their center of mass at the center of the object. And so they can be treated like discrete particles. Meaning that if I had a square, then some uniform square, it can be treated like a particle with a mass at its center. Or I have a disk or a sphere, it could be treated as a single particle with its total mass at its center. And then this would work out the same way. If I have some axis of rotation, then I would have my, R in this case being from the axis to the center of mass. So this applies not just to discrete particles, but also to, say, larger uniform objects where you then just find the center of each object and then you can add up their individual moments of inertia. Okay, so that's the first method for discrete particles. So the next method for calculating moment of inertia, and the last one that we'll talk about in this part 1 of the video, so method 2, is what's called the parallel axis theorem. And the parallel axis theorem, this is going to apply to uniform objects, not non-uniform densities, but uniform objects that have an axis of rotation that is parallel, hence the name parallel axis theorem, parallel to an axis passing through the center of mass. So this is easier to understand if we look at the equation and then a corresponding example. So the parallel axis theorem is as follows. We have I sub p, the moment of inertia we're trying to find, is going to be equal to ICM, the moment of inertia for an axis through the center of mass, plus capital M d squared. So again, I sub p is the moment of inertia we want to find. I center of mass is the moment of inertia for the axis passing through the center of mass. That's parallel to the axis that we have. M is the total mass of the object. And d here is the distance between the two axes. So it's the distance between the center of mass, so your new axis, and the center of mass axis. So I'm going to box this parallel axis theorem, and then over here I will draw an example of it. So let's look at a sphere where, let's say instead of having the sphere rotate around its center, as it might sometimes do, instead we have the sphere rotate and be pivoted on one end so that our axis is as such, so that the sphere then will rotate around that axis. So this is our axis, our actual axis. Then the center of mass axis is the one that would pass through the center of mass, as if the sphere was spinning around its center. So that would be the center of mass axis. And so d here is the distance between the center of mass axis and the actual axis. So if we knew the moment of inertia for the axis through the center of mass, then we could easily get the moment of inertia for when the axis is shifted by some distance d. So in this case, if we look at this, let's say the example is that it's a uniform solid sphere. Well, we provide you with a table of moment of inertias for common objects, and one of them happens to be a uniform solid sphere. And in that case, you can look at this table that's provided, and you would know that I center of mass is going to be equal to 2/5 times the mass of the sphere times the radius of the sphere squared. And again, this would come from a table that you're provided with. So that uniform solid sphere has ICM of 2/5 mr squared if it was rotated around the center axis. But we've shifted our axis and we've now pivoted it off axis. So the moment of inertia for our new axis is simply going to be I center of mass, so 2/5 mr squared plus the mass of the sphere times the distance that you've shifted your axes. In this case, that's going to just be a single r. So that's going to be equal to 2/5 mr squared plus mr squared. And so we end up with the moment of inertia for this example is simply 7/5 mr squared. And that was for this specific example here. All right, so let's go ahead and do another example using this parallel axis theorem. So what I will do is go ahead and draw out the next example. And in this case, we'll make it a little bit more complicated, and we can see how we can add parallel axes or add things from different moment of inertias from individual objects to get the total moment of inertia of a system. So let's say that I have a long uniform rod, and then at the end, I put a sphere, something like this. And the sphere has a radius r, and the rod has a length L, and it's pivoted at one end over here. So this is our axis. So this is, again, another example. So in this case, we know that we're going to be able to use the idea that we have two objects here. We have the sphere and we have this rod. So if they were both uniform, so let's say here that they're uniform objects, then the total moment of inertia will be the moment of inertia of the rod plus the moment of inertia of the sphere. So I'll just call that I rod plus I sphere. And so we have to just find each of these individually in order to get the main thing. So here I will say I rod. Well, this is a uniform rod pivoted around one end. That's actually a really common object that is also found on that table that you'll be provided. So I'll call that 1/3 times the mass of the rod times the length of the rod squared. So that 1/3 ml squared, that's going to be from the table for common moment of inertias that you'll be provided with. So given that you know that for the rod, then it's a matter of what would be I sphere. Given that the axis that it's rotating about is not the center of mass axis, right? In fact, the center of mass axis for this sphere is shifted over as shown. So the distance between our new axis over here and our center of mass axis, that distance is just happens to be equal to L plus R. So I sphere, we can use the parallel axis theorem. And we can write that I sphere, if we look back at the parallel axis theorem that we wrote down previously, it's going to be equal to ICM plus MD squared. So ICM will be the moment of inertia for a uniform solid sphere rotated around its center, and as we saw in the previous example, that comes from the table as 2/5 mass of the sphere times r squared. So again, that came from the table, plus the mass of the sphere, in this case, plus d, the distance between the two axes. So L plus R quantity squared. So that gives us then the moment of inertia of the sphere and the moment of inertia of the rod. And so we end up with the result for the total moment of inertia of the system is simply going to be 1/3 times the mass of the rod, L squared, plus 2/5 mass of the sphere, R squared, plus mass of the sphere, L plus R quantity squared. And there is no reason to simplify that. You can just leave it like this because the mass of the rod and the mass of the sphere are different, and we're not given the values for L and R. So that is our result for the moment of inertia for that system. All right, so we just learned two ways to calculate moment of inertia. One for discrete objects or uniform objects that can be treated as center of masses at their center. We also know that we're going to be given a table of results for common objects, and we can use that along with this parallel axis theorem in order to calculate the moment of inertia for objects, common objects, but when their axes are shifted away from the center of mass. Part 2 will cover moment of inertia by integration.